So for today, to start out Unit 3, we're going to take a look at some powers again. We looked at things like this, 8 to the third before, and of course that is 8 times 8 times 8, or 512. What we're going to concentrate on today is we're going to concentrate on powers of 10. We've already looked at these a little bit with our place values, but let's look at them a little bit more. Let's say we have 10 to the power of 3. What are we going to get? High energy group. Got 3 tens or 1,000, right? 10 to the power of 2 would be 100. 10 times 10 or 100. How about 10 to the 1? That should be an easy one. That's just 10. 10 to the 4th? 10,000, right? You can see a pattern emerging here. This is 10 to the 3rd. How many zeros were there? 3. 10 to the 2nd. How many zeros? 2. 10 to the 1? 1 0. 10 to the 4th? 4 zeros. What would 10 to the power of 0 be? 1. Very good. Because if we look at our pattern, when we go 10 to the 3rd, 10 to the 2nd, 10 to the 1st, each time we divided by 10. So taking that 10 and dividing by 10 again, we better get 1 for 10 to the 0. We also briefly talked, what's 10 to the negative 1 have to be? 1 tenth. We divide by 10 again. 1 divided by 10 is 1 tenth. 10 to the negative 2, 1 100th. 10 to the negative 3, 1 1,000th. Very good. The pattern that develops here is that 10 to the power of negative 3 is the reciprocal of 10 to the 3rd. It's 1 over 10 to the 3rd. So 10 to the power of negative 6 would be 1 over 1 million. Because 10 to the positive 6 is a million, 10 to the negative 6 is 1 over 1 million. It's the reciprocal. Now I could multiply these out and make that 1,000 times 100,000, multiply them out that way. But it's nice to be able to work with the powers. We briefly looked at what happens when you have x to the 3rd times x to the 5th. What do we get? Well, x to the 3rd is 3 x's multiplied together. X to the 5th is 5 x's multiplied together. If we multiply them all together, how many x's do we have? 8 of them, right? 3 and 5 makes 8. There's a total of 8 x's multiplied together. I have x to the 2nd times x to the 7th. This is 2 x's. This is 7. How many total x's do I have multiplied together right now? 9. X to the 9th. Good. So the shortcut we're finding is 3 plus 5 is 8. 2 plus 7 is 9. So if I have y to the 7th times y to the 18th, I'm going to get y to the 25th. Good. 7 plus 18 is 25. Or z to the 12th times z to the 15th, I'm going to get z to the 27th. Good. That's not so bad. So I can do it with the powers of 10 as well. I can have 10 to the 5th times 10 to the 8th is going to give me 10 to the 13th. Good. What if I was dividing? What if I have x to the 5th divided by x to the 2nd? Yeah, x to the 5th is 5 x's. X squared is 2 x's. We cancel out. We're left with x to the 3rd. And as Jason said, that's subtracting. 5 minus 2 is 3. So if I have y to the 12th divided by y to the 7th, I'm going to get y to the 5th. Very good. z to the 28th divided by z to the 19th. I'm going to get z to the 9. Cool. Next thing we want to look at. Of course, that means if we have 10 to the 8th divided by 10 to the 5th, we get 10 to the 3rd, right? What if we have x to the 3rd to the power of 4? What that means is we have 4x to the 3rds being multiplied together. What's that going to come out to be? Oh, this is 3 x's, this is 3 more x's, 3 more x's, and 3 more x's. How many total x's? 12. No, you're adding 3 plus 3 plus 3 plus 3. Remember, you add the powers when you're multiplying. So when you're doing a power of a power, you're multiplying them. 3 times 4 makes 12. So if I have x to the 8th to the power of 5, this is going to be x to the, what's 8 times 5? 40. Good. Or 10 to the 7th to the power of 3 is going to be 10 to the 21st. There you go. 7 times 3 is 21. So let's take a look at an example here, just to make sure you've got this down. So in this one, there's 2 different things that need to be done. What has to be done first? That's in the parentheses, so we're going to do 10 to the 4th times 10 to the 7th. And we do. 4 plus 7 makes 10 to the 11th. Now, what do we do with that 3? Yeah, 10 to the 11 times 3 is 10 to the 33. Very, very good. Tell me what to do here.
9 minus 5 times 4.
Okay, so we do the 10 to the 9th divided by 10 to the 5th. 9 minus 5 is 4, so 10 to the 4th. And that's still to the 4th power, which is going to give us 10 to the 16th, 4 times 4. What do we do here? Careful. It's going to be 3 minus a negative 6, right? We divide or subtract. 3 minus a negative 6 becomes 3 plus a positive 6, or 9. So that'll be 10 to the 9. The negatives get you, don't they? Then that's 10 to the 9th squared, so it's 9 times 2 is 10 to the 18th. Tell me what to do here. Careful. You're subtracting 5 minus 9.
Oh.
5 minus 9 is negative 4. So it's 10 to the negative 4. Now to the power of negative 3 will be 10 to the... Yeah, negative 4 times negative 3 is a positive 12. So 10 to the 12th. You look confused. Yeah.
I'm listening to her too.
Oh. She saying anything interesting over there?
Yeah, she told me to
Oh, okay.
don't go to the negative.
Yeah, dang it. Okay, I want you to try this one in your seats. Give us one. So you look at this. We're going to first combine those two. What do we get? 10 to the 5th. Good. And then we're going to combine those two. What do we get? -2. Then we'll combine those two. 7th. Very good. Positive 7th. Because 5 minus a -2 is positive 7. And then 10 to the -3. How many you got that? Jonah got it? You got it to work out, Jason?
Yep.
Cool. You know where you went wrong?
Yeah.
Okay. So why do we care so much about these powers of 10? Well, in electronics it comes up. I mean, you guys learn how to get around the electronic stuff without it. But if you're getting into more complicated electronics, you'd need to use it a lot. Let's go back and review our place values here for a second. So we know this is the 1s, the 10s, the 100s, and so on. And this is the 1/10ths, and so on this way. Well, what we have is called a base 10 numbering system, which means our place values are exponents with a base of 10. This is 10 to the 0, which is 1, 10 to the 1, 10 to the 2nd is 100, 10 to the 3rd is 1,000, 10 to the 4th is 10,000, 10 to the 5th is 100,000, 10 to the 6th is a million, and so on. 10 to the -1, we've already seen is 1/10. 10 to the -2 is the 1/100th. 10 to the -3, -4, and so on in that way. Well, a lot of times when we're using larger numbers, like 6,200,000, we abbreviate that by just writing 6.2 million. Well, we can abbreviate that even further by just saying this. Rather than writing out the word million, we can just say, hey, 10 to the 6th is the millions place. So it's 6.2 times 10 to the 6th. That, of course, is our scientific notation. Scientific notation takes the first digit of the number, names its place value. That's the 10 to the 6th or whatever is there. And then we put the decimal point after that digit and express it in that form. For example, I could have 0.00097. That would be written as 9.7 times what place value is the 9 in? 10 to the -4. And that's how scientific notation works. Now, obviously, we don't want to have to draw out this whole number line and write in the place values every time we convert a number into scientific notation. So we've developed a shortcut, like with the 6.2 million here. Decimal point started here at the end of the number, but we wanted to move it here after the 6. So it moved 1, 2, 3, 4, 5, 6 places. Hence 10 to the 6th. Same with this one. The decimal started here, and we moved it to here. It moved 1, 2, 3, 4 places. 10 to the -4. Now, how do we know whether that power is positive or negative? Well, 6,200,000 was a large number. It's bigger than 1, so it has a positive power. The 9,700 thousandths is a small number. It's smaller than 1, so it has a negative power. So if we want to convert a number into scientific notation, like 470 million. Of course, that's going to be 4.7. Put the decimal point there. And then we got to figure out the place value for the 4. Well, the decimal point started here. It goes 1, 2, 3, 4, 5, 6, 7, 8 places. Is it 10 to the 8th or negative 8? It's positive 8 because this is a large number. So this one here is going to be written as 9.2. The decimal point starts out here, and we want it here. It goes 1, 2, 3, 4, 5, 6 spots. 10 to the 6th or negative 6th? Negative. That's a small number, so it's a negative power. It's in the negative place values. Well, we need to be able to convert the other way as well. If I give you 3.9 times 10 to the -4th, can we convert that back into standard or decimal notation? Yeah. You start 3.9. The decimal point has to move how many spots? 4. And is it going to get smaller or bigger? It's a negative, so it's going to get smaller. So we got to go 1. We have to add zeros. 2, 3, 4. Right there. So 0.00039. Now, a lot of people ask, do I have to put a 0 in front of the decimal point? The answer used to always be no, you don't really have to. Now there are a couple of fields out there that are requiring it, like the medical fields are getting really picky about it. So we'll put our zeros there. You might have 7.3 times 10 to the 5th. What's going to happen? How far does the decimal point have to go? It's going to get bigger, and we have to go 5 spots. We go 1, got to add some zeros, 2, 3, 4, 5. So that ends up being 730,000. Simple enough?
Yep.
There are a few pages to go along with this one today. Page 121, exercise 2.4. 1 through 45, the odds. Because you have the answers for the odds, so you can check your own answers.
Oh, all right.
Page 125, exercise 2.5. I gave you that packet at the beginning of the year with all the odd numbered answers in it. That should be for the entire semester.
I thought that was just for the freaking,
First assignment?
yeah, I thought that was just for the freaking unit.
No, that should still be good. And also on page 130, exercise 2.6, 1 through 57. Yeah. Obviously, that's a lot of problems. I don't expect you to do all of them, but make sure you pick through them enough to know what you're doing so you can be prepared for a quiz that might possibly be coming up soon.